morning, good afternoon, ladies and gentlemen. I would like to thank organizers for giving me this opportunity to perform in front of you today. I would like to thank all of you who joined my presentation today. So I will talk about fast time resolved measurement thermometry at nanoscale. The method is developed in my lab in Warsaw. More generally, it addresses thermodynamics at nanoscale. So in next minutes, you will get to know how to extract thermodynamic electron temperature of the nanoscale system by measuring somewhat abstract probability of the switching process. So let's set the problem first. So consider generic problem in which we have a physical body of heat capacity CV, which is kept at an elevated temperature delta T above the above temperature T. It is connected by some thermal link characterized by the thermal conductance with the reservoir. And if we allow now this body and reservoir interact, it will exchange it will give up energy to reservoir, and the rate of the changes of the internal energy will be proportional to departure of temperature in linear regime. And now if we look at the solution of this simple problem, you will find out that the solution is exponential, and the relaxation time is given here by heat capacity divided by the conductance of this thermal link. And the relaxation time for very low temperatures, for electron system, for other phonon systems can be easily as high as above 100 microseconds. But as we rise temperature, it can easily go below 10 nanoseconds. So if you really want to get access to the real-time detection of temperature, if you want to follow the thermal dynamics of your system at nanoscale, you need to develop a tool which would allow you to measure fast thermal transients. And this kind of okay, it's not switching. I can't push my slide. Okay. So this kind of reasoning was provided by Arliu Client some time ago, and he found that such thermometry, that electrical and magnetic investigation are far ahead of thermal investigation, and he attributed this dearth due to lack of fast, robust thermometers that could be easily integrated with nanoscale structures. So if you would possess such thermometer, fast thermometer, what kind of processes I'm talking about? This, you know that at low temperatures, electrons are thermally decoupled from phonons, so they can get extra energy, they can get extra temperature when they are by absorbing photons, but they can also lose energy by emitting photons. Here we talk mainly about, here we talk about this simply black body radiation. They can also lose energy by diffusing into regions of the lower temperature. This is hot electron diffusion characterized by diffusion constant or thermal conductivity. Hot electrons can give up their energy to phonons. Here, electron-phonon coupling plays a role. And finally, phonons in the nanostructures, they don't need to be kept at the same temperature as phonon in the substrate. So here, Kapitsa resistance plays a role. So we can have phonons in the nanostructures overheated over substrate phonons. Finally, the phonons that we excite in substrate, they can travel in the substrate, transferring energy between remote nanostructures, although both these nanostructures are not connected galvanically. And this can give rise to some extra excitation channels for some remote nanostructures, which may be important when integrated many circuits on the same chip. So far, this kind of processes were investigated in steady state. So people assumed some thermal models. They energize structure with some constant signal, heat it with some constant signal, and then they could measure the distribution of the temperature in the sample. And then by assuming some thermal model, they could extract the dynamic parameters, but this was the determination of these parameters was based on model. My approach is different. I want to get access to the dynamics directly. So I want to see how fast these processes are by directly measuring the relaxations. So I hope that I convince you that, okay, we need to have such fast thermometers. So I don't, in this community, I don't need to talk that the thermometry is, okay, we need it for calorimetry, for bolometry. We need it for quantum thermodynamics, which addresses the heat flows, heat transfer due to single particles, due to single quanta, like electrons, photons, but maybe also the superconducting vortices. We should remember that understanding thermal budget in nanostructures is essential for failure-free operation of various nanocircuits involving squids, qubits, some microcoolers, barometers. So the thermal effects, they very often mimic quantum behavior. So we have to keep all these thermal effects under control. Without understanding well the thermal distribution of a structure, you can easily get misinterpret your data. And finally, thermometry. More generally, if you don't want to use notion of temperature for some non-equilibrium processes, the method that I will show addresses also quasi-particle dynamics. And this can be non-equilibrium quasi-particles. And as you know, that also keeping quasi-particle under control is very essential, because quasi-particles, they spoil metrological application of numerous devices like single electron boxes, microcoolers, but they can be used also to our advantage if you, for example, want to use bolometer. So bolometer only works because it absorbs photon, and photon creates quasi-particles which then we can detect. So sometimes they can be used to our advantage, sometimes we would like to get rid of them. But the thermometry, fast thermometry, allows us to study. Okay, so let me introduce the main hero of my today's talk. This is superconducting aluminum nanobridge. It looks very modest compared to structures that you have seen already here in this conference, but it is very robust, and it is used as a working horse in my thermometry. So this is polycrystalline aluminum. This is the simplest type of the Josephson junction that you can fabricate. Here the constriction is 60 nanometers. But I can already anticipate your question. The method will work for any type of Josephson junctions which exhibit hysteresis, either thermal or that arising from running in tilted Washburn potential. But I work with this one. This has many advantages, and this is good to work as a proof of concept. So let's look at the IV characteristic of such junction. It has pronounced supercurrent branch, meaning that we have it conducts supercurrent up to certain threshold. Upon exceeding this threshold, it switches to normal state. It is normal state since after switching, the overwhelming dissipation happens in system, and it very quickly bridged together with adjacent leads is driven to the normal state. Its temperature exceeds Tc. And only upon lowering the bias current, you can reduce the heating to extend that electron-phonon coupling wins, and the junction retraps. But what is important in current context, as you increase temperature, here you have 16 milli-K, this is 1.2 K. As you increase temperature, the size of these supercurrent peaks gets reduced. So this is the principle. We will associate the variation of the supercurrent peak with the temperature. So we want to measure this switching current accurately. What we do, we use switching protocol. We send many testing pulses on the junction. In response to each pulse, junction may switch, then the voltage pulse develops on the junction, or it may remain silent without pulse developing. So then counting number of times a junction switched divided by the total number of pulses sent on the junction gives us estimation for the switching probability. And now repeating this experiment for various values of the testing current pulse, we can measure what is called S-curve. So this is testing current dependence of the switching probability. So this experiment remains in analogy to the familiar tossing coin experiment, in which we toss coin and count how many times we obtained head, and the number of heads divided by total number of trials gives us probability. So in this case, we can measure this, we can tune this switching probability. We can tune it by means of the testing current amplitude, but also by means of the temperature. So, okay, if we measure S-curve at different temperatures, you see that we have, okay, here I measure from 400, these are experimental data, to 800 milli-K with step of 5 milli-K. You see that there is very good temperature sensitivity. And now this set can be already treated as a calibration set of curves for thermometry. So whenever we measure, this probability is not normalized, so this is, here is 1 and here is 0. So whenever we measure, say, half switching probability at this current value, then we can say that, okay, this is 700 milli-K. But we can make also direct experiment. We can just measure the switching probability at constant testing current as a function of temperature. So in such, here you have the uncertainties of the, so measurement is very accurate. My fridge can stabilize temperature. This is at the moment static bath temperature of the fridge. So here what we measure is the temperature responsivity of probability for fixed testing current around 400 milli-K. So if you work with small departures of temperature from the bath temperature, you can use the linear behavior of the probability in this regime to get access to the dynamics of some linear processes. If you now measure this temperature responsivity at different temperature, you will get, you will find that this here is plotted the inverse temperature responsivity. You will find that the best responsivity is obtained at larger temperatures. But this allows you already to trace various linear processes at different temperatures. Alternatively, if you want to get access to nonlinear range of temperature variations, you can measure full critical current dependence on temperature. So here you will find that the decrease of the critical current as you increase temperature, and this behavior can be explained within Ambegaoka-Baratov theory, which you perhaps know from tunnel junctions. Here it also works well because the junction, as I presented, it consists of many transmission channels, but they don't have on average too much transmission, and in such case the tunneling junction formula also fits well. So this is second method. So one is we can get temperature from probability. Here you can get temperature from critical current or from switching current, which is very close to critical current. So now, so far I was only talking about static thermometry. So let's see, but I promise that there will be some dynamic ingredient. So what we do to get the access to the dynamic properties, thermal properties, we use the idea familiar somewhat from laser physics. So we use pump and probe pulse. The pump pulse is intended to energize nanostructure. So after heating part of nanostructure, after some time, which is called here delay time, we send on the junction, which can be in some other place of the nanostructure, testing pulse. And this testing pulse, the probability for switching at this given testing pulse carries information about the temperature. So, of course, to get the value of the probability for a single delay, we have to repeat this process many times, because the probability measurement assumes measurement over ensemble. So method addresses perfectly repeatable thermal processes, which can be restarted many times with the same initial conditions. Okay, so let's have first experiment with this. So you see here we have the junction. Here we measure the temperature dynamics of the bridge itself. So first we energize the bridge, we switch it, and then it cools down back to the bath temperature of 300 milli-K, and in the process of the relaxation, you see that the switching current recovers back to its initial value. We can recalculate this curve into temperature. So this is the temperature profile of the inertially cooled superconducting wire. And this can be fitted here with a theory of one-dimensional heat flow equation involving electron-phonon coupling and hot electron diffusion. So here we can measure this kind of curves at various temperatures. So you see that using this method, determination of the temperature from probability, you can get access to variation at the level of up to 20 milli-K from the bath temperature. Here, these are exponents because we work in linear regime. If you want to extend your measurement beyond the linear regime, then you use the switching current approach. But both these data address the same cooling process. So these data are in fact tails of this, if you would like to, but measured in different modes. So now we can take these times, relaxation times, we can plot them on the curve. So here you get the temperature dependence of the relaxation time of aluminum. Here I fitted the simple analytical model of the electron-phonon coupling. So you see that this model nicely reconstructs the higher temperature behavior, and the model predicts also lower relaxation than determined experimentally, because I have not taken into account here the hot electron diffusion. But this is just to give you a flavor that we can measure relaxation time here at the level of 30 nanoseconds. Okay, and now let's do some experiment, because I showed you the thermal relaxation in the bridge, which works also as a sensor. So this was thermal characteristic of the sensor itself. But now let's do some hot electron diffusion experiment in which we do some thermal excitation of the sample in one place, and we will see its effect in remote place. So here is the sample. Here we have the heater. This is also displayed here on the same photo. We energize the heater by sending short 5 nanosecond long pulse through the heater. We create here quasi-particles. They diffuse through this neck into wire, and then they spread in the wire. Here, I plotted the simple model of free electron diffusion. So we expect that this is Gaussian distribution, which with time should spread around. So in the place where we have injected particles, we expect that the exponential decay of the number of quasi-particles or temperature. But at site here, here is the sensor, 60 micrometers away from the injection point. Here we expect that at first we should see no signal, and then signal should pick up and go down, because of course quasi-particles need some time to get here. So what our experiment tells us, here is the timing of the pump and probe sequence. So we send the energizing pulse. Delay equals 0 corresponds to situation in which testing pulse overlaps with the heating pulse. So it leads to some crosstalk between pulses, but after this testing pulse is outside the window of the heating pulse, you see that there is no signal here. So here, at this moment, hot particles, they had not yet time to arrive to the junction. And only then signal builds up, it goes to maximum after 300 nanoseconds, and then the quasi-particles diffuse away. And this measurement is performed for two polarities of the heating pulse to show you that this effect originates really from the thermal effect, not from some electromagnetic ringing. So where pulses overlap, if ringing happens, then the polarity here of the signal changes. But here you have the same polarity because this is the same effect. So, Okay, let's recalculate now this profiles, these diffusive profiles of quasi-particles into temperature. This is, here we have solid lines are feeds. You can already find with simple model of free electron diffusion and applying Einstein's Smoluchowski law, yes, which tells you that the average squared departure of particles should scale with time. So you will find that maximum with diffusion constant taken from literature should appear after 280 nanoseconds. And here we see 300 nanoseconds. So we see that the time after which we obtain the maximum, it agrees with what we expect from literature. But the point is that here I directly determine this diffusion constant. So I can get access directly to this dynamics. I see this diffusion constant directly. Yes. Okay, so here, if we go to higher, okay, maybe one more thing here. You see that when we go up from 0.4 to 0.6K, the signal diminishes. And this is because the quasi-particles are eaten on the way when they travel to the detector by phonons. And also the heat capacity grows. So it takes more, they lose more energy on heating the electrons that they meet on the way. So the recombination rate gets with temperature dramatically increases and signals goes down. But if we look here, okay, we can measure even at 0.8 small variation. This is only departure from the base temperature 400 microkelvin. And with blur of the signal at the level of 100 microkelvin. So this is, I showed this slide to you to show that I can measure only not fast, but also with very good vertical temperature resolution. Okay. So,
sorry, disturbing, but 8 minutes left.
Thank you. We can also measure, say, two relaxation processes. So we energize structure with one pulse, and then we see single relaxation here. But this is, again, we just test single nanobridge. So we energize bridge and we measure temperature dynamics of the bridge. If we send one pulse, this is simply electron phonon coupling, what we expect. It's 1.4 microseconds relaxation time. It takes this time for electrons to equilibrate with phonons. But if you send many pulses, then the relaxation consists of two exponents. One is fast, as before, with the same decay time, and the other is slow. And this slow is 1,000 times slower than the fast one. And in fact, this is a relaxation of the local phonons in nanostructure with the environment. So this shows that if you overheat significantly your structure, you do, okay, electrons may relax quickly, but you will still need to wait a long time. Here is 1 millisecond before your phonons are cooled down. Okay, and this, now we can analyze at this point. This is, okay, similar experiment. What we do, we send many pulses. This is the phonon temperature dependence on the number of pulses that we use to energize the junction. So we measure the temperature 10 microseconds after last pulse, meaning that electron relaxation to phonon subsystem is over, and now we see only phonon temperature. And you see that with adding each pulse, so few pulses is still okay, but then we start to add more pulses, the phonons temperature rise to some elevated value, and if you go to this value, then you need to wait for 1 millisecond to cool down back. Okay, so this is also important issue. You may ask whether the temperature that I measure is thermodynamic temperature, and or it is some okay, not defined value. So here what I did, this is again this diffusive profile that I have already presented, and what I did here at this point A, B, C, D, E, F, G, I measured S-curves. At this particular delay, I measured S-curves, so they are plotted here at this different point. And then I can also measure the same S-curves in the static mode at given buff temperatures. Here they are measured to each 2 millikelvin. Yes, so very good temperature stabilization of the fridge. And now it turns out that I can impose static S-curves on these dynamic S-curves. They look exactly the same. And if we assume that the S-curve is a unique fingerprint of the quasi-particle distribution, then we should conclude that the quasi-particles in this state are described with well-defined Fermi-Dirac distribution as they were in the static case, meaning that in this case, I can convert this data into thermodynamic temperature. Okay, so I would like to leave some time for questions. I showed you this, how to monitor fast thermal transients in time domain with switching thermometry. I can obtain excellent resolution, which is 2 orders of magnitude improvement over the state-of-art mesoscopic thermometry. Of course, it addresses perfectly repeatable thermal processes, so it is not single-shot method. But if you can restart your system many times, you can get access to this very fast dynamic. It is applicable to all Josephson junctions, as I explained, and it has also this good vertical resolution. So I would like to thank, these are my friends working with me on this thermometry. Here is Marek, who is with us also here, senior researcher, and this is my PhD student. We have also very nice, my friend collaborator from low temperature laboratory in Finland. So this is the core of our team. And I would like to also advertise our poster in which we investigate the vortices with the same nanobridge. So we have here confined vortices, and we can, with this switching method, we can see them, and we can also, in future, we will be able to measure the thermal effect, dynamical thermal effect. We have already such data resulting from the moving of vortices in these boxes. So you really, to do this, you need access to, yes, you need to stay below 100 nanoseconds to see this. Okay, thank you very much.
Thank you very much. Now talk is open question. Any question from on-site participants? No question. So is there any question from remote participants?
So far not, but maybe I can ask a question. You showed this heat diffusion pulse, and you compared it to the diffusion equation using the Fermi velocity. And from that, you would expect it would be temperature independent, this peak. But it was slightly, but systematically shifted in temperature for this temperature. Yes. So the peak position.
Yes.
Yes.
So the point is.
So what? You have an explanation for that?
Yes. So explanation. So this is, you see, this is full model. This is full model.
Yeah.
So this is solution of one-dimensional heat flow equation, taking into account the temperature dependence of thermal conductivity kappa, electron phonon coupling, and then this peak is reproduced well. So the point is here that this peak has no time here to develop to its full scale, because the hot electrons are annihilated by phonons, and also due to increased role of heat capacity. So simply, okay, this peak would like to grow higher, and then it would have the maximum slightly farther. Remember, here is logarithmic scale, but it cannot arise to its full height, because before it's able to rise, it's cut by phonons.
Yeah, but I was more concerned about the peak position at the time when it occurs, the maximum. So the simple theory wouldn't predict a shift in the position, right?
Yes, because a simple theory like this one, Einstein-Smoluchowski, is free particle diffusion, meaning they don't interact. So just, you inject them and you look how they spread, being given diffusion constant. But if you switch on the dissipation mechanism, then of course you expect that, they are annihilated, and then the picture changes. So, here you see that you may say that, but this is logarithmic scale, yes? So we it's not fit actually.
Yeah.
We applied the parameters of as they are given in literature, and this is what we get. So here you may say that the signal is arrives slightly faster, but this can be, for example, due to thermal conductivity of aluminum, which is better. But this we didn't want to manipulate, yes, because here to make such fits, we use one set of the fitting these functions, thermal functions. We don't change them from curve to curve. So the potential actual fitting would involve the manipulation with the functions with these thermal parameters, which are given as temperature functions, yes? In fact, thermal conductivity, electron phonon coupling, yes.
No, sure.
They are not single parameters. They are, of course, functions of temperature.
Yeah. Okay, I see no further questions from the participants.
Any question from on-site? Okay, thanks, speaker again.
Thank you very much.